Hello APC Mechanics students in Unit 4 System of Particles and Linear Momentum, Class 2, 4.1 Center of Mass, Part 2. Then Section 1, Uniform and Non-Uniform Mass Distribution. In the previous video, we have determined two different techniques in order to determine the location of center of mass for finite distribution of particle-like objects and for extended objects of uniform mass distribution. So today we're gonna introduce a new notion related to non-uniform mass distribution. Previously we have seen how to locate the center of mass of an extended object of a uniform mass distribution. In the following section we will introduce a new notion related to locating the center of mass for a non-uniform mass distribution. And in order to do so we need to introduce a new quantity, which is the density. The mass distribution is modeled by a quantity known as the density. We can define three types of densities, and this depends on the dimension or dimensions of our problem object. Let's start with the first dimension, one-dimensional object. For a uniform mass distribution, now let's suppose we have the following bar. Now why this bar is considered to be one-dimensional object? Because, or we're assuming that the thickness of the bar is not much important for us. Now for a uniform mass distribution, let me say it has a mass m and a length x. Then we define the linear mass density to be lambda given by m divided by x, where lambda is the linear mass density in kilogram per meter, m is the mass of the object in kilogram, and x is the length of the object in meters. In this case, lambda is constant because the mass distribution is uniform. Now, why here lambda is constant? Lambda is the linear mass density, which gives us information about the mass distribution. Because we're assuming that this is uniform, uniform means the same, which means that the mass at all points along this object is concentrated the same. For this reason, lambda in this case is constant simply because the mass distribution is uniform. Now for a non-uniform mass distribution, we have the same bar, but here notice that the bar has been represented by gradient color, which means that the mass distribution is not the same. You can think about it. Here, the color is saturated on the right more than the left, so here we have more mass. Let's say, for example, we define the linear mass density according to what? Now let's consider a small infinitesimal part of this rod or bar. You can choose it anywhere. In this case I have chosen it to be in this place. It has a certain mass given by dm. Now dm is just to indicate that this mass is very small and of a very small length dx, and in this case for this particular point chosen along the bar or along the rod, the linear mass density is given by dm divided by dx, where lambda is the linear mass density, dm is the differential mass, and dx is the differential length, and all the units that we have discussed previously, they hold perfectly the same. In this case, lambda is variable because the mass distribution is non-uniform, and this is straightforward. Now if you choose another point here, which is more to the left, you can expect that lambda won't be the same because lambda gives us information about how the mass is distributed along the bar. And we know that this is a non-uniform mass distribution. The mass is not concentrated the same everywhere, which means lambda would be variable. Now for a two-dimensional object, for uniform mass distribution, this is a two-dimensional object that lives in a plane, has length and a width. It has a mass m, it has a surface area s. For this reason we can talk about something called the surface mass density given by sigma, which is m divided by s, where sigma is the surface mass density in kilogram per meter square, m is the mass of the object in kilogram, and s is the surface area of the object meter square. In this case, sigma, which represents the mass distribution over surface area, in this case would be assumed to be constant. Now what about non-uniform mass distribution represented by the gradient color? We define the surface mass density by choosing a certain point along the surface area, having a mass dm because it's a very small mass and very small area. Now this shape here is exaggerated in a sense that for a small particle-like point extracted from this object, it should be very extremely small. If you look now at this, it has certain dimensions it should be even more smaller than this one. Now in this case, the surface mass density is given by dm divided by ds, where sigma is given by kilogram per meter squared. Dm is the differential mass in kilograms and ds is the differential area of the object. In this case, as anticipated, sigma is variable because the mass distribution is non-uniform. If we choose another point here and we calculate the ratio dm divided by ds, we're gonna find that sigma is not the same at this point. Now moving on to three-dimensional object. For uniform mass distribution, we have the mass, we have the volume, then we can define the density. The volume mass density, rho, is given by kilogram per meter cube. M is the mass of the object in kilogram. V is the volume in meter cube. In this case, rho is constant because the mass distribution is uniform. For a non-uniform mass distribution, represented by gradient color in this case, we define the volume mass density after we specify a certain infinitesimal part of this object, represented by differential mass dm by differential volume dv. Rho would be given by dm by dv. All SI unit that we have discussed at the top, they hold perfectly the same. And in this case, as we said previously, that rho would be variable because the mass distribution is non-uniform. Now what we have done in this section, we have introduced the three different quantities related to mass distribution. Now we're ready to locate the center of mass for non-uniform mass distribution. A bar of non-uniform mass distribution lambda and of length L is shown here. We are interested in determining the center of mass of the bar. The symmetry trick doesn't work here because, so we cannot say that the center of mass is at the middle of the bar. And by this I'm referring to the symmetry trick, which is related to the geometry, simply because the mass distribution is not the same. Simply because, okay, the mass distribution is not uniform, the way to approach this problem is to divide the bar into small differential infinitesimal parts of masses dmi. Now, this would be one of them, dm1, dm2, dm3, dm4, and you can infinitely divide this bar into the masses dm1, dm2, dm3, dm4, etc. until we reach dm infinity. So you can think about it collecting points like this. So as you collect points infinitely, you can construct a rod of length L or a bar of length L. Now let's choose the origin to be the left edge of the bar. Then each mass dmi is at position xi from the origin. Then this differential mass m1 with respect to this origin is located at a position x1. This dm2 is located at a position x2. This dm3 differential mass 3 is located at a position x3. And similarly for dm4, but I haven't represented them here in order for the figure to stay neat. And now let's determine the center of mass. After we have divided the bar into infinite number of points like particle object, we can use the center of mass formula, or the barycenter formula that we have introduced in class 1, which is given by the summation of xi dmi over the summation of dmi. So this can be written as x1 dm1 plus x2 dm2 plus until we cover all points of the rod. Here we have only 4 points, but this is not the case. We need to sum up till infinity. So m1 plus m2 plus etc. As the bar to be divided into infinite particles dm1, dm2, dm3 until we reach infinity, we need to sum over infinite number of particles over the length L of the bar from 0 to L. In this case, the infinite sum operator should be promoted to be an integral. Hence, our center of mass formula will look like something, or will look like that. So the trick here that we're doing, since I is being summed from 0 till infinity, then this can be replaced by a continuous sum, which is known as the integral, and we know how to integrate. And here let me point out something very important. What does the denominator represent? So you can think about it, if this is a linear function here, which is 1, a constant function, which is 1. Then the integral of 1 would give you the variable itself, which is m. So this represents the total mass of the rod or the bar, where integral from 0 to L dm represents the total mass of the rod. Now we're ready to solve the following problem. Consider a bar of length L of a non-uniform mass distribution whose linear density lambda is given by lambda is bx squared, where b is a constant coefficient and x is the distance from the left end of the bar. Now here, as you can notice, that lambda is a variable, so we should have represented the bar with a gradient color, but that's fine as long as we're understanding what's happening. So we have a non-uniform mass distribution given by lambda bx squared. B is a constant and capital L is the length of the bar. Now in part A, they're asking us what's the unit of B. B can be determined by referring to dimensional analysis. So B can be isolated to be written as lambda over x squared. Lambda is a linear mass density, which is given by, so linear mass density has unit of kilogram per meter divided by meter square, and that would be kilogram per meter cube. Then B has unit of kilogram per meter cube. Now in part B, we need to calculate the mass of the rod. Now here we don't know the mass of the rod, but as we have discussed previously, the mass of the rod can be determined from the integral 0 to L dm. Now let's choose the origin to be the left end of the bar as stated here. Consider the infinitesimal mass dm at a distance x from the origin. So we have chosen a small mass belongs to the rod of mass dm and a distance x from the origin. The mass of the rod is given by the continuous sum of all the infinitesimal points of the rod, each of mass dm, and this can be utilized as an integral from 0 to L dm. The problem here is that the boundaries and the variable, they don't agree. The boundaries refer to the position where the variable refers to the mass. So either we need to change the boundaries, or we need to change the mass into the variable, which is the distance, and this can be done by referring to the formula given by lambda as dm by dx. Now if you isolate for dm would be given by lambda dx, and lambda can be rewritten as, so let me state it here, lambda can be written as bx squared dx. Okay, so dm would be replaced by lambda dx, which is bx squared dx. Now b is a constant, can be dragged out, and we're left with an integral in which the boundaries and the variable, they totally agree. Now x squared would give us x cubed over 3 computed from 0 to L. B is a factor, and in this case the total mass of the rod given in terms of its length is given by bl cubed divided by 3. Then the mass of the rod is given by bl cubed over 3. Now here let's do the following check. How come this is a mass? Now we can do dimensional analysis. B is given by kilogram per meter cube from the first part, and L cube would be meter cube, so meter cube with meter cube would cancel, and that would be kilograms. Now moving for part C, we need to determine the location of the center of mass. So here we're talking about non-uniform mass distribution, and we need to use the integral version. Now the downstairs integral already has been computed, and it's given by bl cubed over 3. Now it's left to compute the upstairs integral, and it's x dm. We're gonna follow the same trick here. We have, so basically in the boundaries we have length, and here the variable is mass, so we need to convert this to be length in order to agree with x and the boundaries, and this can be done by referring to the linear mass density. Already now at this point we know that because lambda is given by dm divided by dx, so basically we can isolate for dm, and dm would be given by lambda multiplied by dx, and lambda is given by bx squared multiplied by dx. So here we have lambda replaced by bx squared. Now we have x cubed. B is a constant, can be dragged out. Now x cubed would be x power 4 over 4 computed once at L and once at 0, and that would be bl to the power 4 divided by 4. Now, till this moment, we didn't compute the center of mass. We have computed the integral found upstairs, and already we know the integral that's found downstairs. Now, the center of mass would be the ratio of the first integral over the second integral, which is bl power 4 divided by 4 over bl cube over 3, which gives us 3 over 4l. Now, let's take a look at the following result. They're telling us that the center of mass is found in the third quarter of the length. So the center of mass would be found somewhere here. And why this is anticipated? The linear mass density is proportional to x squared, and our origin is chosen here. So as we're moving toward the right, the linear mass density is telling us that the mass becomes more and more concentrated. So if we split the bar into half, this means the right part has more mass than the left part. For this reason, we can anticipate that such a result is reasonable. Then thank you for watching and see you soon in a new one.